Greetings, everybody. So here's a problem you'll find on our assignment, and in some ways it's like some others that have come before it. It involves a cylindrical tank. It has some kind of fluid in it, and we want to calculate the work done in removing the fluid from the tank. Okay, so that much it has in common. What's different about it is the orientation of the tank. Okay, so the tank might be a cylinder, but rather than standing upright, it's laying on its side horizontally. So that's what makes it different. And let's talk about how to do it. So here's how I envision the problem. I have a little sketch here, and it's not to scale, but it has all the right stuff on it for us. And the way that we set up this kind of problem is we imagine that there's this tank, whatever its shape is, it's full of fluid of some kind. And since work is force times distance, some force makes something move a certain distance, that's the basis for how we calculate work. So we apply that force times distance model to some imaginary cross-sectional slice of our tank. We say if that cross-sectional slice were the fluid, we'd have to lift that up to a certain point and calculate the work done on doing that throughout the whole tank. Okay, so what I need to do in this case, since it says that this tank has a radius of 7 feet, but we want to lift or pump the fluid out of the tank to a point 18 feet above the tank, then I need to take this cross-sectional slice and I need to lift it up to this point where y is equal to 25. As it is, I've laid the tank on its side. I have the y-axis right through the end of it. 0 there is right in the middle of this circular opening or circular side of the tank, and it has points at 7 and -7 on the y-axis, and we're going to pick up to this point where y is equal to 25. Okay, all right, so that's how we envision the problem, and I focus on this cross section for my setup. Now I'll go through the setup as thinking about that way, and then when we're done I'll go through the basic model. Okay, and then you could look at it either way from there. Okay. All right, so think about this cross section. I need to figure out how much work is involved in lifting this up to that point where y is equal to 25. And in doing so, I need to calculate the force required to lift it, which is going to be its weight. Okay, so to get that, I need to know its volume. So imagine there's this cross section. It says this tank has a radius of 7 feet, and this direction here is 14 feet. Okay, so what I don't know about that cross section is this side of it. I know this side's 14 and I don't know that one. If I could tell you how big this side was, then I could tell you its volume. All right, okay, so let's think about like this. This side, or this side, being that that cross section will be a rectangle, is what you see right here up against this circular end of the tank. Okay, so I've drawn the circular end of the tank, and then in red I've sketched like what that cross section looks like as it goes up against it. And I see the cross sections are wider in the middle and they get narrower towards the top. But this distance here that I'm looking for varies as you go through it. Okay, so how am I going to tell you some kind of formulation for this side of our cross section? So given that this is a cylinder, it does have this circular shape at its end. Okay, and it has a radius of 7. So this circular end of the tank has an equation, as I have it right here. X squared plus y squared is 49. That's a circle with radius 7 and center at the origin. Okay, and remember the y-axis is going right through this thing with 0 on the y-axis in the middle of the circle. Now I want to know this distance here, okay, or this distance all the way across, either way. And if I take this equation for this entire circle, radius 7, and I solve it for x, then I will get this distance here, which is half of what I want. Okay, why does solving this equation for x get me this distance? Well, on our graph here, this distance is a left and right distance. So if my equation tells me where all the points are, x and y, up, down, left, right, that's what x and y do. If I solve it for x, I find the distance to the right. Okay, like you tell me the y on the y-axis, and this formula tells me how far over there it's going to be. Now that's what I want. Now if I double that, then I get this entire side that I'm looking for. So here goes. The volume of this cross section right here is 14, which is this side, 2 root 49 minus y squared, which is this side, and then dy, which is our imaginary thickness that the cross section has. And that will be in cubic feet because all of our measurements are in feet. Okay, so now I know the volume of the cross section. From there, what do? I need its weight. Because I'm going to pick this cross section up, I need the force required to do that, and that will be its weight. So I was given that this tank has some fuel in it that is 52 pounds per cubic foot. And I know how many cubic feet our cross section is. So if I multiply that by 52, think about how the units work out. 52 pounds per cubic feet and times cubic feet, that cancels to give me pounds. Okay, so all right, the weight of that cross section is 52 times 14 times 2 root 49 minus y squared times dy, or 1456 root 49 minus y squared dy. Okay, so now I know the force required to lift our imaginary cross section that this whole thing is based on. Now, how far up do I have to lift it? The question says that we want to pump the fuel out to a point 18 feet above the tank. Maybe that's where the engine is. Okay, there's the tank and it pumps the fuel out to some engine. Okay, so I want to pump it to some point 18 foot above the top. So if the top is at 7, then 18 feet above that is at 25 on the y-axis. Okay, so here's what I do to tell you how far this imaginary cross section needs to be lifted up to remove it from the tank. Then I have to take 25 minus y, where y is the point where this cross section is at on the y-axis. It's a some y coordinate. If you take 25 minus that y coordinate, you get the distance all the way to the top where you want it to be. So that's how far you're going to lift it. Now at this point, I know how heavy the cross section is, okay, and I know how far I need to lift it, and that's all we really need to know, because work is force times distance. Okay, so I take the force, that's this, also known as the weight in this case, and I take the distance, that's this, and then you'll get this integral right here. The bounds on the integral have to cover the geometry of the tank top to bottom, and then that is -7 up to +7 on the y-axis. Okay, so there's our setup. We got our integral. I might do one more thing. I might multiply through here and distribute so I can get 2 terms. Okay, so now solving this problem comes down to solving this integral. Let's look at that. So to solve this integral that we have at this point, for this problem, let's do it this way. Let's just use integration formulas because there's so much other stuff that goes into this problem for the setup. Let's just use formulas to solve the integral. Okay, so here they are. Here are the integration formulas for our problem right here. I have root a squared minus y squared dy. In our case, that is this one here where a is 7. And then I got y root a squared minus y squared dy. And then that's this one where a is 7. So I can use this one in its formula for this first one, and I can use this one for the second one. Okay, we're going to do it like that. Now, if you're solving this on the quiz, then you could use some online calculator that does the integral for you, but on the test, the browser's locked down, so just have these formulas ready as part of your notes. Okay, unless you want to work the integrals from scratch. This one's done by trig substitution and this one by u substitution. Okay, so there goes. Now here are my antiderivatives or solutions to the integrals. Okay, that should be y right there. I made a mistake. I accidentally wrote an x. Okay, so that should be a y. Okay, it comes from this right here, so it should be y. And then I evaluate. A lot of this cancels out. We're left with this, and it rounds out to about 2.8 million foot-pounds. Okay, all right. So that's how you work it. I want the emphasis to be on the setup and the conception of the problem, and just use the formulas here to solve the integral once you get it set up. So that's kind of the way you see that we have it, is the setup is one part in this problem, at least the way it is in my math lab, and then the solution, the calculation for the work, is the other. Now notice there's some units there. Let's talk a little bit about the units and the general model. Okay, so here's the general model as it could apply to this kind of problem. Whether this tank is a cylinder or a rectangular box or something like that. Okay, so we've got some tank that has some three-dimensional shape. Okay, and we're going to put the y-axis going right through the middle of it. The tank spans from its lowest to highest points from y is a to b on the y-axis. Okay, all right, and somehow we figure out a formula for the area of a cross section of this tank at point y on the y-axis, and that's going to be a of y. This will be a function of y because it will probably be that the cross sections are different sizes as you go through this tank. Like on my cylinder, they're largest in the middle and they get smaller towards the ends. All right, but nonetheless, you've got your 3D tank, whatever geometry it has. You figure out some formula for the area of a cross section that's located at point y on the y-axis. Okay, and you want to lift or pump the fluid up to some point c on the y-axis. All right, well then here's your integral for work. Y minus c, a of y. You have to have a factor in there for the density of the fluid, whatever that is, dy. That encompasses all the elements that I have incorporated up here. I just didn't tell you why they come together. Okay. All right, so that's it. Now about the units, notice that question on up there from my math lab has part of the answer is to indicate the units. All right, foot-pounds in this case. Well, the way that'll work is we may have different units. And we'll just say if distances are in feet in the problem, like in my problem it says, well, the tank has a radius of 7 foot, something like that. If the distances are in feet, the density will be in pounds per cubic foot, and then the work will be in foot-pounds. Okay, just because when you multiply distance times force, that's the way it cancels out. Okay. And the other case would be that distances are meters, and accordingly density of the fluid that you're pumping, that you're lifting, is going to be in newtons per cubic meter, and in that case the work will be in joules. A joule is a newton meter. Okay, again, work is going to be force times distance, and in this case that's going to work out to be newtons for force, meters for distance, joules for work. Okay, all right, so there it is. Now this problem, focus on the setup. I'd like you to understand all the components involved in the setup and how you put them together. And then I'm not worried so much about the integral from there. I hope that will be the easy part. Keep those formulas handy if you expect to see this again. And of course, if you need any help, let me know.